This P7 video is about stellar coordinates and the apparent motion of celestial objects. So what we're going to look at first of all is how we define the coordinate system for locating objects in the night sky. And for that we need to understand something called the celestial sphere. So what we've got here is the Earth with the equator in red, and we have the North Pole, the North Celestial Pole, and the South Celestial Pole. There's no real difference between this and the standard rotational poles of the Earth. Okay, we're just projecting them out into space basically. And then we need basically two coordinates to specify the position of a star in the night sky. The first one of these is called right ascension, and that's basically a distance along the Earth's equator measured in hours. We'll talk about how we define 0 hours right ascension in a second, but for the moment we're just going to have 0 hours indicated by the direction of the yellow dotted line, and then one complete rotation is 24 hours, so 6 hours is a quarter rotation, 12 hours half, and 18 hours 3/4. And the red line is just called the celestial equator, which is just the projection of the Earth's equator onto the celestial sphere. Okay, you can see the two basically line up. So that's right ascension, and just useful to remember that the Earth's rotational direction is shown by the arrow on here, so it rotates towards the east. Okay, so the other coordinate that we need is basically called declination, and that works by being 0 degrees at the celestial equator, plus 90 at the North Celestial Pole, and minus 90 at the South Celestial Pole. So that gives us our two coordinates for locating a star in the night sky or any other object. Of course, it doesn't locate it in three-dimensional space. For that, we'd also need to have the distance of the star away from Earth, and that would then determine its position in 3 dimensions. Okay, so let's have a look at what this looks like from an observer's point of view. So what we've got here is that the yellow dot on the surface of the Earth is an observer, and the dotted lines show the field of view they're looking at, and the white curved rectangle, because it's projected onto the celestial sphere, shows the area of the sky that this person is looking at. Okay, I'm going to put two stars in for reference, a blue star and a red star. The blue one to the top right just here. Okay, and the red one sort of in the bottom towards the middle. So what does it look like if we were to look at that? Well, what we've got then is the horizon. So the brown is basically the ground, and then you can see that the 0 degrees declination line, the red celestial equator, goes pretty much through the middle of the field of view, and there it is on our axis, and runs from about 0 hours to 6 hours. Now the thing is flipped so that the 6 hours is on the left in the view picture, because obviously we're looking from the other side of this image. If you were standing at the yellow point on the Earth's surface, then it would be left-right flipped. Okay, so and then we have minus 10 degrees declination line below the celestial equator and plus 10 above. Okay, and we can also label on this diagram which directions things are in. If we're standing in the northern hemisphere looking towards the equator, then we're looking south, and east will be on the left and west will be on the right. So what happens then when we allow sort of time to progress forward? Well, you should know that stars in the sky and everything in the sky appears to move from east to west, so things rise in the east and set in the west. We won't really get any rising and setting in this case, and that should be familiar to you, because if you're very near the poles like we are here, then the declination lines are pretty much parallel to the horizon, and that's the reason, for example, that you get the sun not setting when you get very close to the pole, because it follows these lines, as do all celestial objects. So let's just run it forwards now. We're going to run it forwards 2 hours. I'm just going to point out a couple of things before we start. So at the moment, the blue star is at approximately 5 hours right ascension. Now, the thing that people get confused about with this is the star coordinates are fixed in this system. So that blue star will always be at 5 hours right ascension. And what happens is, due to the Earth's rotation, the entire coordinate system and all the stars rotate, okay, in the sky, due to the Earth's rotation. So it's an apparent movement because the Earth is the thing that's moving, but that's what happens. So the entire thing shifts east to west. And when we run this, you can see the shift of the field of view on the left-hand side and what it would look like on the right-hand side. So we're going to imagine that you're standing in this location, not moving. So you're staring straight forward at what is currently 3 hours right ascension, and this is what will happen in 2 hours' time. Okay, so here it goes. It's shifting over. The entire coordinate system is rotating. You're still looking straight forward, and you can see that what was 3 hours right ascension in another 2 hours is now rotated round to 5 hours right ascension. This is why we use hours on the right ascension axis, because it basically is very useful. If the star you're looking at or if the star that you're interested in is 2 hours further round in right ascension, then in 2 hours time, if you look in the same direction, you'll be looking at it. Okay, so that tells you the amount of rotation you're going to expect. Right, okay, so that's the basic idea of right ascension and declination and how the system works. Just to clarify again then, it's the coordinates of the stars are fixed in this system and the Earth rotates within the system. Okay, so let's have a look at the difference then between what it looks like at high latitudes near the pole and at low latitudes near the equator. Just in case you get given a picture and it looks unfamiliar. So we've already seen the high latitudes near the pole picture, and at low latitudes then basically you're able to look further south. If you are further south near the equator, you're able to look further south when you look at the horizon, and that means you're looking at a lower declination or a more negative declination. And so near the horizon you'll get these much more curved arcs, and this makes sense as well because we know that if we go down, say, as far as the UK, then we see sunrises and sunsets. We are not in that circle around the pole where the sun never sets, or at least doesn't set except seasonally. So we will see the east-west motion, but now the curves mean that things will rise in the east and they will set in the west. The stars, the sun, the planets, everything will rise in the east and set in the west. Okay, there'll be slight variations that we'll discuss in a second, but the basic pattern is still the same. So, a couple of things to note then, where the position of the pole star, we're going to look at this in a second. The pole star, or Polaris, is the star that is directly above the north celestial pole. So that means that it isn't affected by the Earth's rotation because it's at the centre of that rotation. So it is utterly fixed, and always you will, if you're trying to go north, that's the direction to go in towards the pole star. So in the right-hand picture where we are near the pole, right, then the pole star will be almost directly overhead. But when we go closer to the equator, and we're looking south, sort of towards the equator, then the pole star will be low down towards the north horizon, which is the one that would be behind us on this picture. Worth bearing in mind, of course, that if you were to look east-west, then actually what you would see here when you're near the equator is the stars rising almost completely vertically off the eastern horizon, going almost directly overhead, and then setting on the western horizon. So that's the motion of celestial objects, the general motion of celestial objects. Just to show you how this works in a real situation, this is one of these time-lapse photographs. So how this has been done is to point a camera at the pole star, which is in the middle here, which I said before is the centre of the rotation, because it's on the celestial pole, and all the other stars will then rotate around it. So these stars are actually tracing out lines of constant declination. Okay, and you can also tell how long the exposure is. If you take a particularly bright streak, I'm going to do this one down the bottom here, there's the start of it, and it rotates around to there. You can see that that's about a third of a full rotation, which means it's approximately a third of 24 hours, so it's about 8 hours of exposure. That makes sense because you're not going to get, you won't be able to do an entire rotation, obviously, because the sun will rise, and you won't be able to therefore see the stars. They'll be too dim to see against the background of the daytime sky. So that's how what we've talked about relates to these time-lapse exposure pictures that you can see. Okay then, so what about other objects apart from the stars? The other objects do show slight deviation from this following lines of constant declination behaviour. The sun, for example, we know that the sun is low in the sky in the winter and high in the sky in the summer, and that's because of the Earth's tilt and the Earth's rotation around the sun. So during the summer solstice in the northern hemisphere, the sun is at plus 23.5 degrees declination, so it follows that declination line and therefore goes very high in the sky. September equinox, it's at 0 degrees declination, so it's lower. And then, of course, lowest of all in the winter, it's at minus 23.5 degrees. So it doesn't get very far above the horizon at all. And then back to the March equinox, it's at 0 degrees declination. So basically, the maximum and minimum declination of the Sun correspond to the amount of tilt of the Earth's axis, which is 23.5 degrees. That makes total sense, okay? So the Sun basically follows the declination lines, but it follows a slightly different one every day as the Earth orbits around the Sun and the tilt changes. Okay, so the Moon. We know that the Moon orbits in the same direction as the Earth's rotation, and this is linked to the whole lunar day issue, which is discussed in the sidereal solar and lunar day video, and therefore it takes a bit longer to move across the sky than the stars because it's slightly sort of counteracting the Earth's rotation with its motion. So it follows the declination lines basically, but it doesn't go as swiftly as the rest of the night sky. Planets, of course, also shift. Due to both the Earth's orbit around the Sun and their planet's individual orbits around the Sun. And again, there's some complex behaviour there, and that retrograde motion is one example of that. The planets don't all exhibit retrograde motion, only Mars outwards. And again, there's more detail on that in the retrograde motion video, but it's just to show you that all of these things are basically caused by the same issues. It's just the relative motion of the Earth and the object in question. And even nearby stars we know exhibit parallax. That's our method of measuring the distance to them. They vary very slightly against the fixed background of stars. They don't quite follow the same pattern, okay, over the course of 6 months. So it's a very slight change, but it's there. And the basic rule of thumb is that the faster an object is moving relative to the Earth, the more it deviates from following the lines of constant declination, and also the nearer the object is, because it's an angular thing that we're doing here, and we know that objects that are nearer when they move have a bigger shift in angle. Okay, so that's some of the deviations from the straightforward behaviour of following the declination lines. Just a little couple of notes here. Unlikely that they'll ask you this, but just in case you're confused about how we know which direction 0 hours right ascension is in, that was the dotted yellow line that we saw on the first image. I'm just going to show you how they do this. It's useful to know as well, and we can see also how the seasons work, although it's not strictly on the syllabus. You should know that anyway. So what we're going to do here is we're going to have a view looking down on the plane of the solar system. So I've just got this picture of Earth from the side here, and the blue arrow is showing where we are looking from on our main diagram. So there's the Sun in the middle, okay, with the Earth's orbit marked in blue. If we're looking down on the plane of the solar system, then basically the North Pole is pointing very slightly out of the screen here, and the South Pole into the screen. And because of the Earth's tilt, we can see the equator as well. And so in this image, we've got the northern hemisphere tilted away from the Sun and the southern hemisphere tilted towards the Sun. We rotate round 3 months later. Neither hemisphere is tilted towards the Sun, so we get what's called an equinox, which is where there's equal length day and night. And that makes sense because in the previous slide we talked about how the Sun is at 0 declination in this situation. And that means it'll spend an equal amount of time above and below the horizon, therefore equal day and night. And then we get the opposite situation to our first image here, with the northern hemisphere tilted towards the Sun and the southern hemisphere tilted away, and then another equinox, another 3 months round. So points to note about this then, that obviously we should know that it's winter in the northern hemisphere when the northern hemisphere is tilted away from the Sun, and it's summer in the northern hemisphere when the northern hemisphere is tilted towards the Sun, and it's obviously the opposite season in the southern hemisphere. And then we can fill in the intermediate seasons just by the order. So because it goes autumn, winter, spring, summer, then spring in the northern hemisphere comes after winter and before summer, and autumn in the northern hemisphere comes after summer and before winter. And we can then put the months on. December is the middle of winter in the northern hemisphere, then March, June and September. And this is how we define 0 hours right ascension. We need a fixed direction in space, and the one that has been chosen, this is an arbitrary choice, there's no particular reason to choose this rather than any other direction, but it's easy enough to define, is that the yellow arrow here is the direction of 0 hours right ascension, and that is the direction the Sun is in during the Earth's March equinox, okay, which is sometimes called the vernal equinox in the northern hemisphere. You might have seen that labelled on some diagrams. So that is the fixed direction of 0 hours right ascension, okay. Now, how does that affect things? Well, Another thing you are required to know for the specification is why we can see different stars in the night sky at different times of year. Now, this is fairly obvious, but it gives us an opportunity to illustrate what we mean by the direction of 0 hours right ascension. So I'm going to kind of combine those two things to help you try and understand it. So we're now going to look at the solar system from the side. And we have to remember the very important point that stars are only visible at night. And this is the crux, the most important point about why we can only see different stars at different times of year. So here's the sun, now with the Earth's orbit viewed at least partially from the side. So we're seeing it, we can see that tilt directly now from the side. And again, we're just looking at the same situations as before. We'll look at December, March, June, and September, just like we did in the previous diagram, looking from the side rather than the top now. And because of what we talked about in the previous one, we can now fix the directions of the right ascensions, okay? Because 0 hours right ascension is from the March picture of the Earth towards the Sun, that means 6 hours is pointing off to the right in this diagram and 18 hours off to the left. As we said, 0 hours is pointing out of the screen, which means 12 hours is pointing into the screen. Now what we're going to do is blank out the night side of the Earth, okay? Which of course is the one always pointing away from the Sun. So in December, on this picture, it's the dark side of the Earth is pointing, the middle of it is pointing towards 6 hours right ascension. In March, you can't see the dark side of the Earth because it's the one that's pointing into the screen, but that is obviously therefore pointing towards 12 hours right ascension. In June, the dark side of the Earth points towards 18 hours right ascension, and in September, the dark side points towards 0 hours right ascension. Now remember we said that the coordinates of the stars are totally fixed, apart from those ones that wander about due to a tiny bit of parallax, but the coordinates of the majority of stars are totally fixed in this system, which means that the dark side of the Earth is pointing at different stars. And because we can only see the stars when we rotate into the dark side of the Earth, that means we will see different stars during different parts of the year. We'll see the stars in December that are in the portion of the sky that is in the 6 hour right ascension region. We'll see the stars in June that are in the 18 hour right ascension region. That's the reason why this works. And that's true for both southern and northern hemispheres, we should note. It is also true, of course, that we can see different stars in the northern and southern hemisphere all year round, simply because the northern hemisphere never points far enough south to see the stars in the southern sky. So that's a separate issue, right? But this issue about why we can see different stars at different times of the year is all to do with the rotation of the Earth about the Sun. Okay, so that's stellar coordinates and some associated little bits and pieces from the Naked Eye Astronomy section of the syllabus.